Hello, welcome to this lecture series on electronic properties of materials. This is lecture number 3. In this lecture I am going to discuss Drude-Lorentz model, also called Drude's model, and it is often called as classical free electron theory of metals. In the last lecture I have discussed how to calculate number of free electron per unit volume and what is the expression for conductivity or the electron density. Okay, so to calculate electron density we need number of free electron per unit volume, okay, and the charge of the electron, which is already known. Then we require the average velocity with which the electron is moving in the presence of the electric field strength, say epsilon. Okay, so we need a method to find the average velocity of the electron in the presence of electric field. Okay, so to get the value, right, many people have tried, and the method or the model which is widely accepted is Drude's model. This model is actually proposed by Drude. Okay, then Lorentz introduced some more information on that, so the model is actually called as Drude-Lorentz model. Okay, what is Drude's model or classical free electron theory? First I will discuss the postulates or assumptions in Drude's model. Then we will see how Drude's model explain the electrical conductivity of metal and thermal conductivity of metal and other properties. Okay, yeah, so what are the postulates or assumptions? Postulate number 1. See, in the last class I have told you when metallic crystals are formed, okay, each atom lose one or more electron, and these electrons will move around the crystal lattice like a gas enclosed in a container. That's why these electrons are called as electron gas. These electrons are called free electrons, or also be called as conduction electrons. Okay, now what are the postulates? See, in Drude's model, the free electrons also called conduction electrons are responsible for electrical conductivity and partly responsible for thermal conductivity of metals. Okay, free electrons are responsible for electrical conductivity, and the free electrons partly responsible for the thermal conductivity of metals. Why partly? We'll discuss as we go along. Right? Then, second point. Free electrons in metals are assumed to be non-interacting classical particles. These free electrons in metal, okay, are assumed to be non-interacting classical particles. Free electrons in metals are assumed to be non-interacting classical particles. First of all, I like to describe, or I like to give the meaning for the non-interacting particles. So what is the meaning for non-interacting particles? Non-interacting particles. What is the meaning? Non-interacting means there is no attraction or repulsion exists between the electrons or between electron with the ion cores present in the crystal lattice. Okay, so non-interacting means there is no electron repulsion exists in the lattice or exists in the crystal. Okay, electron do not repel each other. And another point, there is no electron ion core. Okay, ion core, you know very well, in metal, when metal atoms combine to form metallic crystal, each atom will lose electron, 1 or 2 electron, and become ions. These ions occupy the crystal lattice. Okay, and the electrons that is released, they are called as free electrons. There is no attraction. There is no electron ion core attraction exists in the crystal. So there is no repulsion, there is no attraction. That is the meaning for non-interacting particles. Okay, so free electrons in metals are assumed to be non-interacting classical particles. So non-interacting means no repulsion, no attraction. Okay, repulsion between electrons, attraction between electron and positive ion core of the crystal lattice. Clear? Then what is the meaning for classical particles? Let me write the next page. What are called classical particles? Right? See, the free electrons in metals are assumed to be classical particles. Right? If I say a particle is classical particles, then they follow Newton's laws. Okay, if I say the particle is classical particles, they also obey Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution or statistics. Since it obeys Maxwell-Boltzmann distribution, I can say that you can very well apply kinetic theory of gases. We can very well apply kinetic theory of gases for these electrons to find the average velocity. Okay, and remember, there are a lot of free electrons present in the crystal lattice. Okay, I have told you in the last class that per unit volume has roughly, say, per centimeter cube volume has roughly 10 power 22 electrons, roughly. So you can imagine, or you can compare the free electrons in metal like ideal gas in a container. Okay, so these classical particles of the electrons behave like classical particles. These electrons can also be considered as ideal gas. Okay, we can consider those electrons as ideal gas particles or simply ideal gas. Okay, they behave like ideal gas. Then next important point is free electrons. Say there is no interaction. Okay, interaction means no attraction, no repulsion, but the particles undergo collision. Free electrons undergo collision. Okay, free electrons undergo collision in the crystal lattice. What collision? Listen, these electron, okay, undergo collision with the ion cores, electron and ion core collision, okay. Electron collision is neglected. Why? Because the electrons are very, very small. So the electron collision, okay, is neglected in a Drude model. Okay, in Drude model only electron ion core collision is considered. So electron moves in the lattice and undergo collision with the positive ions present in the lattice. Clear? And this is just a collision like normal two bodies which undergoes collision, right? In classical mechanics you might have seen that. Then next point. So this collision, I'd like to give one more information here. The collision that occurs here, which completely randomizes the velocity of the electron. Before collision, see, before collision, electrons move in straight lines. Electrons, GHT, straight lines. Electrons move in straight line. But once the collision occurs, what will happen? Electron move in straight line. Not only that, we are going to see that velocity of the electron keep increasing in the presence of electric field. But what happens once the collision occurs? Collision completely randomizes the velocity of the electron. Okay, let me write that point here. Collision completely randomize the velocity. Completely randomize the velocity of the electrons. Okay, right? So since the electron velocity gets randomized, therefore we can say that some average velocity exists, okay, for the free electrons in the presence of some the applied electric field. Okay, so this point is very, very important. This point tells some information that there exists an average velocity, okay, in the presence of average velocity of electron in the presence of electric field. Clear? Then next point. Yes, point number 4. Mean time interval between two collisions. So collision occurs, right? Suppose if you have a positive ion core, an electron moves, okay, and collide with this positive ion core. Then after collision, the electron again moves and collide with another positive ion core. Okay, so what is the time taken between two successive, and it undergoes collision again here, right? So what is the time taken between two successive collision? Listen, some electron should travel long distance to undergo consecutive collision, but some electrons undergo shorter distance and undergoes collision. So this collision time is not same for all the electrons. Okay, so we require some average time. So on average, what is the time taken for two successive collision? Okay, let me represent that quantity as tau. Okay, so mean time or average time, mean time interval between two successive collision, okay, is represented as tau. So tau is nothing but, okay, mean time interval between two successive collisions. Okay, why we are taking mean, average? The reason is not all electron take same time to undergo consecutive collision or successive collision. Okay, some electron travel long distance and undergo successive collision, whereas some other electrons may undergo shorter distance and undergo consecutive collisions. Okay, so for successive collisions, the time taken for electrons are not same. So that's why we require mean. So mean time interval between two successive collision, right? I'm going to represent that value as tau, also called relaxation time. This quantity is also called relaxation time. Clear? It is also called relaxation time. Now, suppose if electron is moving in the time interval dt, okay, an electron is moving in a time interval dt. In this time interval, is there any what is the probability that the electron can undergo collision. Okay, probability for an electron to undergo collision, probability for an electron to undergo collision in time dt is, what's the probability? Probability for collision, I'll put COLL, that means probability for collision. Probability for collision within this interval dt is dt by tau. Dt by tau, this will give you the probability for the collision, right, for an electron in the time interval dt. Remember, if dt is greater than tau, okay, if the time interval is very long, right, compared to the average time, then definitely their collision exists. So if dt is above greater than tau, okay, collision definitely occurs. Collision definitely occurs. If dt is less than, okay, or equal to tau, in this case probability for collision can be obtained using this formula dt by tau. Okay, this is a very important point, keep this in mind, right? Yeah, so the collision, the successive collision, the mean time interval for two successive collision is tau, and the typical value of tau for most metals, is in the range 10 power minus 14 to 10 power minus 15 seconds. This is a typical value of tau for most metals. Okay, then what is the mean time or mean distance, also called mean free path? What is the mean free path of electron, okay, free electron in the crystal lattice? Mean free path, let me represent that as L. Mean free path is nothing but the average velocity with which the electron is moving. So I'll just put V. V means average velocity into the time required for collision. Okay, see, when electron move to a time interval of tau, definitely collision will occur. After, right, exactly at tau, collision will occur. That's what the tau says. Clear? So V into tau will give you the mean free path of electrons. What is mean free path? It is the distance or average distance traveled by an electron for two successive collision. Clear? Then next point number 5. So I have given information about probability of collision. Okay, then now we are going to, okay, so these are all the essential points you should keep in mind. And one more point I like to give here, sorry. Since the electrons in metal, the free electrons in metal behave like ideal gas. See, free electrons in metal behave like ideal gas. Okay, we can apply kinetic theory equations for these electrons. Okay, and electrons are, you know very well, electrons are like mono atomic particles, or it is a single particle. Therefore, only translational kinetic energy exists. So, from Maxwell-Boltzmann distribution, you can say that, or you can get the equipartition principle. By making use of equipartition principle, we can say that the average energy of an electron, average energy of an electron at temperature T, is equal to, since the gas behave like ideal gas, okay, what is the average energy of an electron? Average energy of an electron at temperature T is equal to, there are 3 translation degrees of freedom possible. Okay, for each translation degrees of freedom, the energy is half kBT, of kB into T, where kB is Boltzmann constant, T is temperature. This is this is the average energy for 1 degree of freedom, but free electrons, they can move freely throughout the lattice. Okay, it can move freely in all the 3 dimensions. Therefore, there are 3 degrees of translation degrees of freedom possible. So the average energy of each electron is 3/2 into kBT. Average energy depends only on temperature because the electrons behave like ideal gas. Clear? So keep all these things in mind. Now what I'm going to discuss is that how Drude model explain the electrical conductivity in metals. Okay, so now we'll discuss about electrical conductivity in metals. What is the Drude's explanation or Drude model's explanation? Okay, Drude's explanation for the electrical conductivity of metals. Right, listen, in the okay, let us consider we'll take some metallic conductor. Okay, so you take some metallic conductor, right? Just for understanding purpose, I'll take a one-dimensional conductor. Okay, you take a wire, imagine like a wire, right? Let us apply an electric field epsilon to this metallic conductor. Okay, so let an electric field, let an electric field strength applied be epsilon. So epsilon is the electric field strength we apply. Now when you apply electric field, what will happen? The electron starts to move in one direction, correct? And each electron experiences some force called electrical force. So what is the force experienced by the electron? Force experienced by the electron, by an electron, is equal to, is nothing but charge on the electron into the applied field strength epsilon. So E into epsilon will give you the force experienced by an electron. Okay, since these particles are classical particles, they also obey Newton's laws. Therefore, from Newton's law we can say that force is equal to mass into acceleration. Here m is the mass of electron, a is the acceleration of the electron. Okay, so m into, we can write acceleration as dv by dt. Okay, and this force and the electrical force, they are actually equal because we are assuming the particle as a classical particle. So therefore I can write m into, first I'll write this, m into a is equal to E into epsilon. Okay, the electrical force experience is equal to the force formula which we use in Newton's equation, correct? So from this we can say that acceleration is equal to E into electric field strength divided by mass of the electron. This is the acceleration, right? We can also write this equation as m into a is nothing but dv by dt. Remember, these velocities that we are discussing here, they are all average velocities. Okay, mass of the electron into dv by dt equal to E into epsilon. Okay, I'll take this as equation number 1. Now listen carefully. Charge on electron is a constant. When you apply a constant electric field strength epsilon, then right hand side quantity become a constant. Okay, for a constant epsilon, if epsilon is constant, right, for a constant epsilon, then E into epsilon is a constant. So if right hand, so Okay, therefore right hand side is a constant. If right hand side is constant, definitely left hand side must also be constant. I have told you m is mass of electron. Mass of electron is a constant. Let us assume mass of electron is a constant. Therefore the acceleration must also be constant. See what I am trying to say? E into epsilon is a constant. Right hand side is constant. Therefore left hand side must also be a constant. Since m is a constant, the acceleration must also be constant. Keep this in mind. Acceleration constant means as the time progress, dt will increase. If dt increases, correspondingly dv also must increase. Then only acceleration remains constant, correct? So what I am trying to say here is, as time progress, as time increases, okay, the velocity of the electron also increases. Remember, velocity that I mean here is the average velocity. So as the time increases, velocity of the electron increases. And you know very well, current density is equal to number of free electron per unit volume into charge on the electron into the average velocity. So what happens if velocity keep on increases? If velocity keeps on increases, J will increase. Okay, current density will increase. But it was found experimentally that current density, after a fraction of second, current density become a constant. Current density is a constant for a given material at a given temperature. So that means, okay, we need to put another term, okay, such that the velocity should not increase continuously. Okay, so what I'm trying to say here is that, listen, as time increases, according to this equation, V should increase. If V increases, J should increase. If J increases, conductivity should increase. But you know very well, at a given temperature, a given material or given metal has a constant conductivity value. Conductivity value is not increasing continuously. So that means there exists some other force, okay, which will make the electron to attain some constant value. Okay, the velocity of the electron will attain some constant value. So in order to explain that, Drude introduced a term here. So m into dv by dt. So what Drude said is that, yes, as the time progress, velocity will increase and it reaches a saturation value. Okay, according to Drude, see, as time increases, okay, V increases, no doubt, but it attains a constant value. It attains a saturation value. It attains a saturation value. That is the idea given by Drude. So in order to attain the saturation value, okay, he introduced a term here. What is the term? M into dv by dt equal to E into epsilon minus, he introduced a new quantity term here, gamma into V. Okay, gamma is a constant, okay, for a given material, for a given field strength epsilon. Gamma is a constant in the given field strength, right? And see here, as V increases, so you are subtracting this quantity from this. As V increases, what will happen at one particular value of V? These two become equal, because this is a constant. As V increases, these two become equal, so it becomes 0, right? That means the acceleration become a constant, or velocity remains constant. I'm very sorry. So velocity remains constant. So to keep the velocity to attain a saturation value, Drude introduced this term gamma into V, where gamma is a constant characteristic of the material and the characteristic and the applied field strength. Clear? Okay, I'll take this as equation number 2. M into dv by dt equal to E into epsilon minus gamma into V. Okay, now listen, at steady state, right here, at steady state means once the saturation velocity is attained, right, what will happen? These two quantities become equal, so this become equal to 0, right? So at steady state, E into epsilon minus gamma into V, this quantity becomes 0. We call that state as a steady state, right? And here this velocity, let me write it as Vf. Why? Once the steady state is attained, you will get the saturation velocity. Let me represent that saturation velocity as Vf. So what is Vf here? Vf is nothing but saturation velocity. Velocity, also called final velocity. Okay, when you apply an electric field epsilon, okay, initially the velocity will increase, then it will attain a constant value, maximum value. That maximum value is Vf. Okay, no further increase in the velocity occur. And remember, Vf is a constant. Is a constant at a given epsilon value. For a given electric field strength, Vf is a constant, right? If I rearrange this equation, we can write this as E into epsilon equal to gamma into Vf, or Vf equal to E into epsilon by gamma. This is one relation we get, right? We can also write this equation as E into epsilon equal to gamma into Vf. What is gamma? Gamma is equal to E into epsilon by Vf, right? Vf is the final velocity or final average velocity of the electron in the applied field strength epsilon. Clear? Right? So keep these two quantities in mind. Now let me go to equation 2 again. Go back to the equation 2. So in equation 2 we have m into dV by dt equal to E into epsilon minus, we have gamma into V there. So in the place of gamma I'll put this. So E into epsilon by Vf into V. Keep this in mind. Vf is a constant, whereas this V, okay, that keeps on increasing. This is a variable. This velocity is a variable, whereas this velocity is a constant. Okay, now I'll take E into epsilon as a common term here, dm into dV by dt equal to E into epsilon. I'll take E into epsilon as common. You'll get 1 minus V by Vf. Okay, now let me rearrange this equation. So I'll bring this 1 minus V by Vf to the left hand side, and I'll bring m by dt to the right hand side. So what we get is dV by 1 minus V by Vf, okay, equal to, and this side we have E into epsilon by m into dt. Okay, now let me integrate this equation. So what we get if I integrate this equation, to find the final average velocity, right, we need to integrate this equation, right? So on integrating the equation, right, so integral dV by 1 minus V by Vf equal to E epsilon m, these are all constant, I'll keep it out, into integral dt. Okay, you know, well, you take this quantity as x, so integral dx by x is ln x, so you'll get ln 1 minus V by Vf. Okay, and we have 1 minus Vf term is there, right? So if you integrate, 1 minus Vf will exist in the denominator, so if you bring it to the numerator you'll get minus Vf. If you want to check, you just differentiate this, you'll get this expression. You just try. Okay, if you differentiate this, see, Vf is a constant, don't worry about that. Okay, you know, really logarithm of x, if you differentiate, ln x is 1 by x, so you'll get this one. Then if you differentiate x, we have minus 1 by Vf, so 1 by Vf cancel, you will get this quantity, right, equal to E into epsilon by m, integral dt is t, and we'll introduce some integration constant c here. Okay, I'll take this as equation number 3. To find C, to find the value of C, put time equal to 0. Put t equal 0. If t is 0, this becomes 0. If t is 0, listen, if t is 0, then the average initial velocity, let us assume, see, t is 0 means we have not applied the electric field, correct? That's the meaning. T is 0 means the electric field is 0. Electric field 0 means the electrons move randomly in the crystal lattice. So on average, the velocity of the electron at time 0, you can assume it as 0. Therefore, V is also equal to 0. If V is 0, this becomes 0. So you'll get ln 1. Ln 1 is also 0. So left hand side quantity becomes 0. This becomes 0. So therefore, it indicates, or it gives that C value should be equal to 0. Clear? Okay. So this is a very important thing. You just keep it in mind. Okay. Then we also know that right. So let me write this expression. See, C is 0. Therefore, I can write this as minus Vf into ln 1 minus V by Vf equal to E into epsilon into m into t. Okay. I'll bring this minus Vf this side. So we can write this as ln 1 minus V by Vf equal to, I'll bring this minus Vf this side. So I'll get minus E into epsilon by m into Vf into t. Okay. I'll take this as equation number 3. Sorry, equation number 4. Running equation is 4. Now, from Newton's law, we know that the final velocity V is equal to initial velocity u plus acceleration into t. V is equal to u plus at is the famous Newton's law, right? Where u is the initial velocity, v is the final velocity. Keep this in mind. Here, the velocity that I mean are average velocities. This is initial average velocity. This is final average velocity. Okay, you know very well the initial average velocity is 0. Initial means before applying the electric field. Before applying electric field, the electrons move randomly. Therefore, the average velocity of the electron is assumed to be 0. So, now when you apply electric field, students observe carefully. When you apply electric field, so this is 0. When you apply electric field, okay, electrons move. When it will undergo collision, once the time becomes tau, definitely it will undergo collision. Okay, probability of collision is 1, correct? Because probability is nothing but dt by tau. I have told you already. If initial time is 0 and if the time approaches tau, then tau by tau become 1, so definitely collision will occur. Clear? Once the collision occurs, the velocity never increases. I repeat, suppose listen, an electron is moving and we have a positive ion core here. It is going to collide. Okay, so the time taken for collision, definitely collision will occur when it moves to a time interval of tau. Correct, definitely collision will occur. Listen, when the electron moves, velocity will increase. Once it collides with the positive ion core, then the velocity of the electron gets randomized. Okay, this has happened for all the free electrons. Therefore, on average, the velocity of the electron will attain a final value. Let me take it as Vf. Okay, when this happen? This happen when time approaches tau. When time approaches tau, correct? And Vf equal to, what is A? A is acceleration. We had I have told you about the expression for acceleration. Here acceleration is equal to E into epsilon by m. Okay, I'll introduce that here. So in the place of A, I'll put E into epsilon by m into tau. What is tau? Tau is the relaxation time. Clear? Or we can write tau is equal to m into Vf, bring m here, m into Vf by E into epsilon. This is the expression for tau. tau is nothing but relaxation time of the electron, or we can say mean time interval for an electron, to undergo successive collision. Clear? I'll take this as equation number 6. Okay, we had equation 4, equation number 5. Okay, now I'll go back to equation number 4. So what is equation number 4? We had ln 1 minus V by Vf equal to minus E into epsilon by m into Vf, E into epsilon by m into Vf into T. Clear? Now see here, m into Vf by E into epsilon is tau. Here we have E into epsilon by m into Vf. So it is nothing but reciprocal of tau, correct? So this equation now become 1 minus V by Vf can be written as minus. So we have T here, and this quantity can be written as 1 by tau. Right? Or if you remove log, you'll get 1 minus V by Vf equal to E to the power minus T by tau. Okay? Bring this minus V by V plus V by Vf to the right hand side and this quantity to the left hand side. So what we get is, let me do it in the next page. So when you do that, you'll get V by Vf equal to 1 minus E power minus T by tau. Clear? What is V then? Then V is equal to final average velocity into 1 minus E power minus T by tau. We get an expression for the velocity of the electron like this. This is the average velocity of the electron in the presence of the electric field epsilon. Clear? Now if I plot, what does this gives? Right? When you plot V versus time, observe carefully. Suppose if t is 0, if time is 0, if t is 0, then e power 0 become 1. Okay, 1 minus 1 becomes 0. Therefore the entire term becomes 0. So velocity of the electron is 0 when time is 0. As the time increases, okay, here we have exponential power minus, so this will decrease, but we are going to subtract this from 1, therefore this will increase. Okay, Vf is a constant. See, as t increases, we have e power minus t by tau, so this quantity will decrease, but we are going to subtract this from 1, therefore the velocity will increase. The velocity will increase. Then what happen if t become very high? Say for example, if t approaches infinity, what will happen? If t approaches infinity, e power minus infinity is 0. E power minus this becomes 0, so you will get only 1. So V become equal to Vf. So V value becomes equal to Vf once the time approaches infinity. Not actually infinity, before infinity. Clear? So this is the final velocity of the electron. Okay, this happens, that is V become equal to Vf. This happens right at 1 tau value or 2 tau value or 3 times tau value, like that. Okay, so the final velocity will be reached right within the time interval 2 tau, 1 tau or 2 tau or 3 tau, okay, within or 4 tau, like that. Listen, the tau values I have told you roughly in the range of 10 power minus 14 seconds to 10 power minus 15, which is very, very small, extremely small. So the electron reaches the final velocity in a very small span of time, 10 power minus 14 second. So that's why experimental, when you do experiment, you cannot even measure the increase in velocity, because the moment you apply the electric field, right, the electron will approach the final velocity immediately. So velocity of the electron become constant. Clear? Because the tau values are in the range of 10 power minus 14 seconds, which is extremely small. Right? So keep this point in mind. This is very, very important. So when you apply electric field, velocity of the electron increases, but the increased time, okay, the increased time is extremely small. So within a fraction of a second, it will increase and attain a constant value. Right? Yeah. So this is very, very important. And this is the expression for the average velocity of the electron in the presence of applied electric field epsilon. Clear? Now. So now I'll go back to the current density expression. So what is current density? You know very well. Current density J is equal to number of free electrons per unit volume. You know very well. We can calculate this for a given metal. Okay, number of free electrons per unit volume into charge on each electron into the final average velocity of the electron. Okay, when you apply an electric field strength epsilon, okay, immediately after a few fraction of seconds, 10 power minus 14, roughly in this range, the electron will approach the final velocity. So this is the final average velocity of the electrons. If you multiply these three, you will get the current density. Or I can write this as NF into E into what is VF? Listen, in the just go through the earlier pages. You can find the expression for final velocity of electron. Okay, so let me give like this. See, we have written the expression for tau, right? What is tau actually? One second. Yeah, so we know very well tau is equal to m into Vf into E into epsilon. Okay, from this what is Vf? Vf equal to E into epsilon by m into tau, correct? Substitute this value here in the place of Vf. So we get E into epsilon into tau by m. This is the expression for current density. Therefore, conductivity of the metal is equal to, conductivity is nothing but volume current density J by the applied electric field strength epsilon. Now in J we have one epsilon right here. So this epsilon and this epsilon get cancelled. So what we get is number of free electrons into E is E square into tau by m. Yes, this is the expression which is given by Drude. Okay, so this expression gives the electrical conductivity of metal, right? If you know the value of tau, right, you can calculate the conductivity of the metal. So conductivity depends on number of free electron present per unit volume. It also depends on the relaxation time tau. Clear? Okay, using this Drude calculated the conductivity of the different metals, and those values, okay, are reasonable with the experimental values. Okay, so we get Drude got reasonable values for sigma. Okay, reasonable values means the values are quite close to the experimental value. Okay, so in those days people were so happy about this discussion. Okay, and they most scientists accepted this model, right? But problem comes in the discussion of thermal conductivity that we are going to discuss in the next class. But before going to see that, I will discuss one problem, okay, using the conductivity value. If conductivity is given, you can calculate the value of tau. So we do one or two problems in the next class. Then we'll continue Drude's explanation for thermal conductivity of metals. Okay, yeah, I stop here. Thank you for listening.